So the icosahedron, we want to count its faces and its edges. So what does it have for faces? So as far as visible faces go, let's see, we have this one right here. Put a little highlight around that. And then coming off that, we have 1, 2, 3 more. And then coming off those, we have 1, 2, 3, 4, and let's see, there's another one down there and another one right there that's kind of barely visible. Okay, so what is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So far I can see 10 vertices. And typically the views that are set up for these, there's some symmetry in the background that we can't see. So let's get rid of some of those highlights. Try and envision the back of this shape that we can't see. So I'm going to make some red highlight dots for the ones that are see-through. All right, so in the background, there is this one here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So think about that for a minute. I'm pretty sure there are 10 faces in the back of this thing that I can't directly see, but I can see through too. So I think there's another 10 for a total of 20 faces. And it should have 20 faces because that's what the ICASA stands for. 20 faces. All right, next we're going to try and count vertices. So let's erase what I have here. All right, so vertices are where the edges meet, the points. And I think I will go with my highlighter again for this. Let's use the red one. All right, so facing out toward us, we have 1, 2, 3, 4, 5, 6, 7, 8. And I guess we can see this one down here, 9. All right, so far, visible vertices, we seem to have 9. All right, and then let's erase those. Vertices we can't directly see, but that are in the background. So 1, 2, 3 more back there. And I think that's it. I think with those 3 and the 9 we found here, 1, 2, 3, 4, 5, 6, 7, 9. I think we'll have to get another view to be sure. There's only 3 more for a total of 12. All right, next, we want the edges. And having a 3D one in front of us would be much easier. And maybe you do have one at home. I have a set of dice that is Platonic solids, plus an extra one. All right, so I'm going to get my highlighter in yellow this time for edges. So I've got this, oops, on yellow, sorry. I have this one kind of right in the middle there. So there's 1, 2, 3, 4, 5 edges, and then coming off of those, we have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then coming down here, 16, 17. I have 18 visible edges here, I believe. All right, so then I want to count the edges in the background. So I'm going to erase a bit to try and find those. Stick with the same color. All right, so in the background here, for sure, there's those 3 that are kind of sitting in the middle. 4, 5, 6, 7, 8. All right, and then trying to place these back here. There is, so there's got to be an edge connecting those 2 in back. And I'm missing some. There's got to be an edge coming over here. And then there's got to be another edge coming down here. Oops, I forgot to count as I was drawing. And another edge there. Is that all of them? Let's see, what do we got? I'll have to recount in a different color now. Switch to a green pen. 1, straight line. So 1, 2, 3, 4, 5, 6. Those gotta connect 7. Those need to connect 8, 9, 10, 11, 12. I believe there's another 12, but I'm not quite convinced yet. What would that give me? That would give me a total of 30, which is a number we've seen before. Am I missing anything? Did I double count anything? So again, I'm trying to find the edges in the background. Let's erase, re-explore the ones that are fainter in back here. And so, for example, like we see this, oops, let's use a different color for that one in the background, how about red line. So we see this one right here in the background. And coming off of that one are these other 2 edges. And those 2 edges form a triangle that meets a front-facing triangle right here. So there wasn't an extra edge to count up here. Similarly, there's an edge in the background right here, and another one hiding under here. And those 2 edges meet over here on a visible one. Okay, so again, I'm going to draw in the ones that are, I believe, are in the background here. I believe that's all of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I'm pretty sure there's 12 of them in back and 18 in front for a total of 30. All right, we're going to verify this in another way. So let's go back to our table. Oops, wrong page. This way. So 20, 12, and 30. So we already had the 20 there. Now we have, switch to blue, 12, and 30, like that. So some patterns that are going on in this table here. Well, I have these in order of the number of faces, 4, 6, 8, 12, and 20. The vertices and edges, there's some patterns going on. So notice there's the 4 and the 6 here. And then let's see, what other patterns do we see here? This one goes, the cube goes 6, 8, 12. The octahedron goes 8, 6, 12. The dodecahedron goes 12, 20, 30. And the icosahedron goes 20, 12, 30. So there's definitely some interesting relationships happening here. And we're going to look for a couple of them. It turns out that there is a pattern to these numbers when you go from left to right here. That there's a pattern with the numbers 4, 4, and 6 that matches the pattern of 6, 8, and 12. So 4, 4, and 6 are related in the same way that 6, 8, and 12 are related. And so what is the relationship between these? And it turns out it's just a simple arithmetic relationship. And I'll give you a hint. One version of it involves adding those two numbers. So let's see, 4 and 4 gives me an 8. 6 and 8 gives me a 14. What does this other number relate? 8 versus 6, 14 versus 12. Oh, 8 and 6 are the same distance apart as 4 and 12. So I think that if I put an equal there, I can do a plus 2 out there. Equal there, plus 2 out there. Let's check it for another one. Let's pick on the dodecahedron, for example. So with the dodecahedron, if I take the 12 faces plus the 20 vertices, I think that's equal to the 30 edges plus 2. So 12 and 20 is 32, and 30 and 2 is 32. Check it out. So I've checked it for 1, 2, 3, 4 of them. And you can see that the faces and the edges switch between the dodecahedrons and the icosahedrons, so the same will hold true. That one, instead of a 12, 20 is going to be a 20 plus 12. And they have the same number of edges each, which is kind of neat. So that's one of the patterns. The other pattern going on here, to erase some things to see it, involves, if we just isolate the cube and the octahedron, their faces and vertices numbers are flipped, and the same thing is true for the icosahedron and the dodecahedron. Their faces and vertices are flipped. So one relationship is the arithmetic relationship between the faces, vertices, and edges of these shapes. And the other, sneak a new page in here, is the idea of what's called a dual solid. Oops, if I could spell dual, there we go. And the dual solid is related to the relationship between the faces and the vertices. Let's use the dodecahedron as an example, which I have right there. Let's do a simpler example. Let's grab the cube as the example. Version of it. So one way of looking at this dual relationship between these solids is to imagine finding the midpoint of each face. So the midpoint of this face over here is going to live somewhere about there. And then this one has a midpoint that's going to be, think about here. So the visible ones I'll do in red. That one's going to be around here-ish, you think? And then in green, I'll make the midpoints of the back sides, which are kind of hidden behind. I think that one's going to be there. This one's going to be about there. And that one's going to be there. Then what I do is from those midpoints, I connect them with edges. So let's see, let's do red edges to make that happen. So the visible ones were in red. So I'm going to connect those first. All right, and each of those edges, vertices can connect to the other ones too. So this one up here can connect down to that one, and this one can connect down there. And let's see, this one can connect over there. So what else can we do? We can connect this one right there, that one right there. These two connect, and those two connect. And let's see what am I missing. It's not quite right. Oh, these two didn't connect yet. And this one down there has to connect over to there. All right, so let's see. I'm going to make some of these dotted to try, and you might be able to already be able to see what this is. Let's use a medium eraser and a little eraser. All right, so let's see which ones are visible here, which ones are not. Let's see, this one is hiding in the background, so we'll make that dotted. And this is going to be visible, that's going to be visible, that's going to be visible. This is going to be dotted. This is going to be dotted. This is going to be dotted. There, and now I think I got it. Can you tell what that is that I've just drawn there? That, to the best of my artistic ability, is the octahedron. So the dual, I spelled the wrong dual there. There we go. Something's wrong there. The dual of the hexahedron is the octahedron, and we see that two different ways. One way is just from our table, where we just switch the faces and vertices values. Now, physically, what happens then is that's like, again, mapping the midpoint of each face to a point and then connecting those. So that's a physical swap of the face to the edge. So we're just reconnecting those. And so that's the physical relationship, which I think is beautiful, pretty cool. And a similar thing happens with the icosahedron and the dodecahedron. So if we pick on the dodecahedron, so if we found the midpoint of each pentagonal face on this, and we connected all those midpoints together coming around the outside, we would form an icosahedron that lives inscribed in the dodecahedron, and vice versa. If you were to take the icosahedron and make a midpoint for each of those faces and connect them around the outside, you get the dodecahedron. And we can kind of envision that. If you look at the top of this thing here, 5 triangles come together to make that vertex at the top there. And the midpoints of those 5 triangles could be connected to make a pentagon. So we trade all those triangles that meet in groups of 5 for pentagons instead, which is kind of cool.